Okay, welcome everyone to this week's Physics Meets ML. So we're very happy to have Stanislas Polu from OpenAI joining us today. Yeah, so Stanislas did first university in Paris and then went to Stanford. And now after various different positions, he now ended up in OpenAI. And yeah, today we're gonna hear a little bit go on the theoretical side at Physics Meets ML, and yeah, we look into recent work of him and his collaborators, looking at proving statements or mathematical statements and tackling things. So I think a very exciting direction, and we are very much looking forward to your talk. So yeah, please take it away.
Thank you very much. Thank you very much. So as you said, I'm Stan. I work at OpenAI. So I'm going to be presenting. So we just released a few weeks ago a paper that's called Statements Curriculum Learning for Formal Math. But the talk will go from the beginning of our kind of expedition in formal math for the past 2 years, covering also results from our first paper, which is called GPTF. But first, I wanted to give you a little bit of background on OpenAI. So OpenAI's mission is to ensure that artificial general intelligence, by which we mean highly autonomous systems that outperform humans at most economically valuable work, benefits all of humanity. That's a big mission. And one of the modalities we've been interested in the most in past years are generative language models. So these are, we call them GPT, for the name comes from generative pre-training. And those models are, you really can, I'll try to assume that people have no knowledge about machine learning, and so we can dive into details as needed. But those language models are really, you can think of them as massive autocompletes that have been trained on the entire internet. So it's a massive neural network that is consists of weights, and the objective is really, given a sentence, try to predict the next word or the next token. So you can really see them as big, very big autocompletes. So that's an example from GPT-3. This is the non highlighted part is the beginning of an article about nuclear power, and the green part is the generation of the model given prompted with that what we call that prompt, which is the text in black. And so as you can see, those models are really impressive. They are able to generate consistent text. If you read it, it looks legit. Kind of makes sense. And actually, GPT-3, which is our model that we provide through our API, our best model, is when you test humans on that task, meaning that you provide the beginning of an article, you let the model generate the end, you give the ground truth, and you ask humans to differentiate between the two, while non-experts about the subject matter are generally completely incapable of differentiating the generated part versus the ground truth. If you are an expert in a domain, the model will often make some errors that look plausible to non-experts. But as an example, say that Stanislas Polu has created the physics ML meeting is something that is not accurate, but to a non-expert person would look probably plausible because Stanislas is working in ML. And so that's kind of a very impressive technology, and you can do a lot of stuff with that. But those models have also some weaknesses. And this is kind of a prompt I created with a few steps, a few deductive reasoning steps that are very easy. So Jenny has 8 apples. She gives 1 to Tom, 4 to Paul. So she has 3 left. Paul eats 3, gives the remaining back to Tom. So Tom has 2 apples. Tom hits half, so Tom has 1 apple, and gives back the rest to Jenny. So Jenny should have 4 apples. And GPT-3 will say, oh, Jenny has 5 apples. And if you generate another sample, maybe it'll say 4, maybe it'll say 7. So it's a kind of an issue because those models are extremely powerful, but yet on rather simple reasoning tasks, they're not enough consistent yet. And this is what motivated us to explore formal math. Because when you think about it, in games, the DeepMind's result, like AlphaGo, AlphaZero, it's really impressive. You give the model just the rules of the game, and eventually the system is capable of creating a player that is better than human. And playing Go or playing chess definitely counts as really heavy reasoning, right? But at the end of the spectrum, in the informal land, we train on a massive data set, and we try to test on reasoning tasks, and yet the models are still very weak. And so it's interesting to think what differentiates games from the informal setup, text-based setup. And when you think about it, there is many different environments that you can think of that are along that spectrum between games and open text. And you can think about informal math, it's still open text, but kind of a subject matter is a little bit more formalized. You have code generation, where here it's interesting because the outputs are much more formal, and you can leverage unit tests to test whether your predictions are correct. And eventually formal math is even closer to games, because you actually have access not only to unit tests, but to a verifier, meaning that when you generate a formal proof, there is a system that exists that will tell you whether that proof is actually matches formally the statement you were looking to prove. And so in that sense, it's much closer to games, because you have game rules, which is the formal system, and you have a verifier that gives you whether your predictions are correct or not. And that's something that we can try to leverage. And we'll dive into a little bit later into the differences between game and formal math. As you know, we haven't created a formal math AGI yet. And so there's still a long way to go. And there is some very core reasons why games and formal math are still very different, and makes formal math still very challenging. So most of our results, and don't hesitate to interrupt me with questions if you have anything you want to ask about. I'm really happy to interrupt the flow, and it's fine, it's really fine. So we've been working on applying generative language models. This is the kind of the technology and the modality we really care about at OpenAI, to formal math, because it's close to games, for the past 2 years. And we have two main results, two papers. One that is called Generative Language Modeling for Automated Serial Improving, which was 18 months ago, or maybe 2 years. And the other one, the most recent one, Formal Mathematics Statement Curriculum Learning. And they both kind of try to address two main differences between games and formal math in ways that let us make progress in formal math. So first, a little bit of a context on what a formal math environment looks like. So on the left, let me try to get the laser pointer. Yeah, perfect. So on the left, this is a theorem statement in Lean. So as you can see, theorem, there's a name. That's the name of the exercise. It's an Olympiad exercise, AMC 12. And so it says that x and p are reals. X is strictly smaller than 2. Absolute value of x minus 2 equal p. And you need to prove that x minus p equals 2 minus 2p. That's pretty easy. You use this one to remove the absolute value, and then you shuffle around terms and you get it. So the proof of the informal proof is really easy. As you can see, the formal proof doesn't look too complicated. It looks technical, but not necessarily complicated. And so the way the formal system works is that given a statement, you get at the beginning, you get a goal, which is the statement itself here. And what you do is that you apply tactics. Tactics are meta programs that generates artifacts that are understood by the formal system. So one challenge here is that a formal system really operates at a rather low level. You can really think of that as high-level languages, programming languages versus assembly code. The machine understands the assembly code. We use high-level language to write that code or compile that code. Here in formal math, it's kind of the same. You have kernel-level terms, which are very complicated, and you have high-level tactics that let you generate those terms with meta programs. And those meta programs are the tactics. So when you call them, they take the goal as an argument, and they try to generate something that the kernel understands, and that transforms the current goal. So as an example, here there's the ring NF tactic. What it will do, it'll shuffle around that expression. As you can see, it hasn't touched the hypothesis. It shuffle around the expression. Then you have this tactic that say, hey, I'm gonna add an assumption C1, and it's gonna be equal to this. This is the application of a theorem to some arguments. And so as you can see, you have C1 that appears as an hypothesis here. Let's say absolute value of x minus 2 equal absolute value of 2 minus 6. And eventually it calls n linaris, which is another tactic. It's a linear solver, and provides some arguments to kind of hint that tactic in the right direction. So it says, hey, you should use your solver, taking as an assumption in particular C1, and also this term, which is another term that says that says something about those hypotheses. And eventually the kernel system, those things will generate kernel level terms. And eventually the formal system will say, hey, I'm good. I have all the term. I'm able to verify the proof. I have a witness for that type. All the goals are accomplished. And this is a verified formal proof. So really, when you want to do machine learning with this, it really looks like kind of a reinforcement learning environment. You have a current goal and you apply actions and you get new goals and you keep going until the state is you're good.
Can I ask you on that? Maybe you come back to
yeah, sure.
data, so how large is this database of goals or like strategies essentially?
Yeah, so that's one challenge of formal math is that so that's kind of the point of the next slide as well. Okay. On the left, it's the on the left is an informal proof of a rather detailed informal proof of the irrationality of square root of 2, and this is a fair comparison in terms of what that proof looks like in lean. And as you can see, it's complicated, and so it makes a challenge because even using tactics, and those tactics are rather powerful and nice to use, but even with those, it's still very hard to formalize statements. And so formal math is really exciting because it lets you verify mathematics in a very systematic way, but generating the proof that are accepted by the system is still challenging. And so there's many people doing formalization, but yet the state of the math libraries, the formal math libraries associated with each system is limited because of the cost of formalization. There was a result in COC, which is a formal system, about, I don't remember exactly, it's the FlySpeak project. I don't remember exactly the term they were formalizing, but it really took basically, if I remember correctly, 30,000 man hours to formalize that thing. So you go from a paper, challenging result, you really want to formalize it because you want to prove that it's possible. It takes 30,000 man hours to build up the infrastructure, add all the background knowledge you need, and eventually formalize the proof of a challenging math theorem. So it's a massive effort, and so it's the state of those math libraries is definitely lagging behind current state of math for sure because of those challenges. And so as a consequence, those math libraries are rather small, especially in terms of by machine learning standards. They generally have something like 100,000 theorems in there, but many of those theorems are actually small technical lemmas. You can think of it as covering most of the math from the 19th century, and most of the 20th century is left out, let alone 21st century. But there is also some interesting efforts in lean of trying to push, at least make some forays in some precise direction about very recent math results, just to show that it's possible to formalize also recent math. But the coverage of math in general is very sparse. From a machine learning perspective, that means that your training set is small. That being said, when you have a proof like this, you have a lot of back and forth between the formal system and the tactics application. So here you do have a lot of goals and tactic application generated by that simple proof. So you do have a rather large data set of goal. Given a goal, what is the tactic that has been applied to that goal in the math library? That data set can be counted in tens of millions of goal to tactic pairs, which is big, not huge, but big. Okay, so diving into the
question.
Yeah, sure.
So in terms of the RL, what would be the reward function? So how would you know that, what would be a notion to being close to having finished the proof?
So the reward, if you think it as a RL system, it's really that goal, which is the success, which really looks like winning a game in Go or in chess. So you would really just annotate that goal as reward 1, and you could do classical RL on top of that.
Okay, so you, in a sense, you're not rewarding intermediate steps. You're just sort of.
You cannot reward those intermediate steps because you don't know whether you're going.
Exactly.
You first don't know whether they are true, because you can definitely land into falsity here. The formal system will let you land in falsity, just that you'll never be able to prove that state. And you don't know how close or far you are to the final goal. So yeah, you would really mostly can only annotate that final goal as reward 1.
Good.
That makes sense?
Yes.
Yep.
Thank you.
So what are the main differences between games and formal math? So the 3 characteristics of games that are really nice is that, so you have access to a verifier. That's the game engine. That's the thing that says those moves are legit or not, and that says whether player A or player B has won. Your action space is finite in board games or games in general. I mean, not games in general, but at least in board games, meaning that at every goal, at every state, you actually have a finite set of actions, which is a very nice property. And that's one that has been leveraged by AlphaGo. The MCTS search kind of relies on the finiteness of the action space. They really explore most of the possible actions at each state, and the algorithm actually assume that action space is finite. And the other very nice property is that the board games are symmetric in the sense that if you there's zero sum, so if you're playing against I mean, there's always a winner or loser, and playing against yourself actually induce a curriculum that is very interesting. Basically, if you have a very, very, very good player and your machine learning system is very bad, you're not going to be able to learn a lot of interesting stuff because you'll be just crushed by the player in front of you. But if you're playing against yourself, you can create that very nice curriculum that will let you progressively learn new techniques by exploration. So basically, you play against yourself, and because of those things are stochastic, you'll do an action that is slightly different than usual, and it leads to a good outcome, and you'll learn from that. And because you're always playing against yourself, that creates a very smooth curriculum in terms of difficulty that really helps the learning dynamics. So in formal math, we do have access to a verifier, meaning that we have a system that says whether those moves are legit or not. That we have a system that says at the end, hey, you're good. But the action space is infinite. It's enumerable. And so you cannot leverage directly the algorithm that has worked for board games. And that's a real challenge, because at each state, you actually have an infinite set of actions that you can take. You can apply you have a finite set of tactics that you can use, because there's only a certain number of them. But those tactics takes arguments, and those arguments are infinite in kind of space size. To give you an example, if you have to prove, and if you're trying to prove an existential proof, many of those proofs, the most easy way to proceed is to provide a witness and prove that the witness actually checks the property that you're looking for. And so that witness has to be generated. I mean, it doesn't appear anywhere, right? It really has to be generated by the policy or the player or the formalizer. And so that's the challenge that is interesting, is that in the action space of formal math, you have what I call exogenous terms, meaning terms that you've never seen. It's not in whatever you can see about the state of the game or the state of the formal system. The term has to come out of nowhere. And that's one of the motivation of using generative language models, is to have that capability of generating exogenous terms. And then they are not symmetric. And that's a challenge, obviously, because if you have a statement in formal math that is just too hard for you, there is no reframing of the setup that you can make to generate easier statements that will serve as a curriculum. You're just stuck there. You can search for as much as you want. If it's too hard for you, you'll just never get to that final state, and you'll never get any reward for anything. And so you just won't be able to learn anything. So that's kind of an interesting challenge. So access to verifier gives you good data generation, because once you do, you follow trajectory and it leads to a good final state. You know that that data is legit. You can use it as a training signal. Infinite action space makes the search difficult, and non-symmetry of the environment makes the self-improvement much more challenging. So if you compare that to informal text, it's all the same situation, except that you also don't have access to a verifier, meaning that if you're doing informal math, the model may generate a proof. It's an informal proof, and you kind of have no way to verify whether that generation is correct or not, except for a human to look at it. And so that makes the data generation aspects of this even more challenging. That's what kind of motivates our work on formal math. It's first, its closeness to games, but it's also different in two aspects that are also applicable to informal text, which is the final goal. And we use generative language models because of that infinite action space. That's what makes it exciting.
Sorry, I have a question.
Yeah, sure.
Yeah, maybe you already explained, but can you explain again why the action space is infinite in formal math? I mean, if you start from this lean, the example you gave, you have a finite number of tactics, and you have a finite number of objects you can play with. So maybe the action space grows through time, but it's not quite the same as being infinite, right?
Well, I mean, if you see here, so the argument to that theorem takes 2 as an argument. So 2 exists here. You know, there's a lot of 2s in the statements, but really, maybe the right answer might be anything. Maybe the right answer was, 597, and 587 doesn't exist anywhere here. And to make progress, you have to generate that 597. If we think about the irrationality of squatter, at some point, basically, you have to, introducing P and Q as a rational. I mean, as a quotient is kind of comes out of nowhere. It's an idea that is not in the context. It's not you have in the context you have irrationality and squatter 2. So irrationality kind of leads you to maybe introduce P over Q, but in the sense there is many proof where if you need to generate a witness for an existential proof, or if you need to introduce a cut, because without introducing cuts, your proof size would explode. If you need to introduce a smart cut, that cut, which is kind of an intermediate lemma, has to be fully generated. And I argue that the space of those generation is infinite, even if the tactics themselves, the set of tactics that you have access to, is finite. But those tactic takes arguments, and the terms that you provide as argument are drawn from an infinite action space.
Thank you. I get it now. Yeah, that makes sense. Cool. Thanks a lot.
No problem. So how do we tackle that? So as I mentioned, we have that data set of goals, which is the formal goal, and we have tactics and their arguments that are applied to those goals from the math library. And so we're really training our model as a generative language model, so really as an autocomplete. And we provide that prompt. So decal is the name of the statements. So we provide decal, that's a special keyword, provide the name of the statement here. So maybe AMC 2002, or maybe irrational of square 2, whatever. We have the set of goals that have been traced from the math library. And so for each of those goals, we provide, there's a goal keyword, which is a special keyword, and then the actual goal. So here would come the tactic state, so the goal, the informal goal, as we've seen in the example. And then we have a proof step keyword, and then we provide the tactic. And we train the model to, given any subset of that sentence, try to predict the next character, okay? As an example, this is a theorem from MathLib. MathLib is the math library associated with Lean. So the theorem name is topological space, second countable topology, whatever. The goal, pretty complicated, comes here. And the proof step that was applied in the math library there is this thing, exact, with those arguments. And so we train our model to do autocomplete on that. So we train our model as generative language models on that data set. And so once you have that, you already have something that is capable of proving things. How do you prove thing? You take the statement that you're interested about, you give it you give the name here, you take the first goal, you give it to the model, you use the proof step keyword, and you let the model generate a bunch of tactics. Okay, And you go to the formal system, you try to apply those tactics. Some of them will fail, some of them will succeed. They'll give you new goals, and you keep doing that way. And you can basically construct a proof tree search using the model. Each time you apply a tactic and that works, that gives you a new sub goal. You go back to the model, generate more tactic, expand all the tactics that work. It gives you a tree, and eventually maybe you'll find a final goal that is everything is proved. And in that tree, that's going to be a line. That's a line that goes from goal, tactic, goal, tactic, goal, tactic, all the way to we have a proof. Take those tactics together, that's your formal proof. So if training just on that, you're capable of proving things. And that's kind of and why it's interesting here. It's because we're using the generative language models to generate those tactics, so it's capable of generating witnesses. It's really it really addresses in a sense the infinite action space. Basically, you abstract the infinite action space by the distribution that your model gives you for a given goal. And so your model, you're going to sample many times from it. It's going to give you a set of tactics. You're probably not going to sample infinitely. You'll take maybe we generally take something like 16 or 32 samples for each goals. Some of them will fail, some of them will work. And our action space has been reduced from an infinite action space to a finite action space, which are the top 16 tactics that our model thinks make sense. And so in that sense, you can do tree search, and you've kind of not solved, but you've made progress in the infinite action space with respect to the infinite action space problem. So taking that very simple technique, we train our generative language models on the mass library, and we use that algorithm to generate proofs. We actually try to explore how varying different things would impact the performance. So the performance here is on a test set of the mass library associated with a Lean or another formal system. So basically, when we get the formal library, we split a train set and a test set that we keep apart, and we train on the training set, and we evaluate ourselves on the test set. And so what we do here is that we vary the model size. And it's interesting to see that as you grow the model size, you do definitely get better performance, despite the fact that the data set is very finite. So you could expect that bigger model would not help that much because the data set is rather small, but it's common knowledge that bigger is generally better, even on limited data. As you can see, there's a kind of a nice improvement as you grow the model size from 160 million parameters to 700 million parameters. As a context, those model sizes are by current generative language model standards, they're very tiny. The current, as an example, GPT-3 that I showed at the beginning has 200 billion parameters. So 200 times more than this one.
A quick question in terms of, do you do any data augmentation in the sense of like varying the statements slightly? I mean, that 2 that you were showing at the beginning, right? You could, think of varying, and so you could, expand.
So if we take what we are right now, what I just described, if you vary the statement lightly, you don't have training data anymore, right? You could try to, if you vary the statement, you could try to prove it, and eventually you would generate new data if you manage to prove it. But you cannot take the training data and vary it that much, because any variation will probably break the proof in many different ways.
I see.
I've got another question. Sure. Your language model that you're using here, what does it actually output? Does it output characters, and then you have to verify that the output is a valid statement, or does it output, like, the word exact here, for example, in your proof step? Is that output by a single token, or did you output EXACT?
Yeah. So we're using the tokenization that that is used for training on the internet. So these are not exactly characters; they're tokens that are trained using that are defined by an algorithm called BPE. So you can think of them as multigrams. I mean, each token is a bunch of characters, but probably exact is probably one token. But here, this character here is probably one token. This one probably one token. Comma space probably one token. HB is probably just one token. Dot is probably one token, and is and open are definitely one token, because those are common words, and so they get compacted together into one token. But you can think of, theoretically speaking, you can think of them as character by character generation. So you have no guarantee that what's produced here is actually even a valid syntax. And when we started working on formal math, we were actually not even confident that language models were able to match the syntax that is expected by the formal system sufficiently well to even generate syntactically valid tactics. So you definitely have no guarantee here. Does that make sense?
Thanks. Yes, thanks.
And so another things that we did in that paper is to study pre-training. And basically what is pre-training is that you take a model, you pre-train it on a very large data set that is not necessarily directly related to the final task. And eventually you take that trained data set and you continue the training at the end, you fine tune it on the data set you care about. And so pre-training has a huge effect. If you take that 700 million model trained from scratch, you get 31%. If you pre-train it on common crawl, you can think of it as a crawl of the internet, you jump from 31 to 39, which is quite interesting because there's no really good reason to believe that training on, chats about rabbits would help generating formal math proof. But I mean, the way to think about it is that as you pre-train on a large amount of text, there's probably some features that emerges in latent space of the model that eventually are useful and transfer positively to generating formal language.
Right, can I ask a question?
Yep.
Yeah, I apologize. You probably answered this before, but when you measure the performance, do you have situations where there are different types of proofs, maybe one more elegant than another, but you check that whatever it did is correct. So it's not that you're forcing it to look for exactly the proof you had in mind. Is that right?
Oh yeah, that's perfectly correct. We don't match the ground truth proof. We just take the statements. Sorry, and I should have made it clear when we use that test sets to evaluate, we just throw the proof away. We just keep the statements. And we try to generate proof that gets accepted by the formal system. And so the proof that are going to be generated will be different. They'll be interestingly different sometime, and they'll be sadly different at other times, like a bunch of unnecessary steps, a lot of noise. But we really only care about generating a valid proof. We don't care about the aesthetics of the proof.
Oh, thank you very much. Are there cases where it came up with a new, more elegant proof of something, or is that too much to ask?
Oh yeah, so when you did that, when we worked on that paper, we actually generated something like, and we haven't even pushed that effort, but we generated something like 20 or 30 new proof that are not necessarily more elegant, but they led to generating smaller kernel terms. That's what formal people care about, because whenever you start your formal system, you have to reprove everything basically. And so if the kernel term level, if the kernel level terms are shorter, generally it means that you're proving everything takes a lower amount of time. And so people are very pleased when you generate shorter proofs in the sense of the kernel level size of the proof. And our models have been able to generate many proof, not many, but dozens of proofs that actually led to more compact kernel level proofs.
Great, thank you.
So it's sometimes different in a good way, and sometimes different in a very depressing way. If we also ablated, this one is actually you pre-train on common crawl, and then you pre-train on a bunch of code from GitHub, and then you finally fine-tune on your formal system. And here you have a nice boost as well. And finally, we designed that data set, which is a mix of archive, math, LaTeX, archive, white paper, LaTeX, a bunch of GitHub code, and dumps from Stack Exchange, Math Stack Exchange, and Math Overflow. So a lot of math-related data. And so in that model is first pre-train on common crawl, then train again on that dataset web math. And that's what led to our best performance. But to be honest, between GitHub and that, the difference is hardly significant. 1% here is not that big. But the idea here is that you do get kind of nice transfer from pre-training, especially focusing on, if not math data, code-related data to the formal system, which is kind of a surprising and interesting. Another result that speaks to the value of doing formal math is that this is kind of shows the improvement in performance as you increase the number of attempts of proving a statement. And as you can see, we have a pretty smooth improvement in terms of performance as you increase the number of samples. What it says here is that it is very simple, is that because you have a formal system, you can really rely on it to help you to decide whether something is good or not. So instead of trying to prove something once, you just tried it many times. And by trying it many times, eventually, by a little bit of luck, you'll land on the right proof. And that luck is actually pretty following if you are able to plot in your head, what you can see here is that it follows a power law. So if you plot in a log scale the number of attempts and you plot the performance here, it's a straight line. So basically, every time you double the number of attempts, you kind of increase the number of the performance by a fixed amount of time, which is exciting. That means that if you throw more compute to the problem, you get a better performance. But it's a power law. So eventually you'll run out of compute before maybe eventually finding your solution. Cool. So going back to, so really that first paper was really about addressing that infinite action space. So we have that formal system, we have goals, and we have tactics that takes arguments that may be exogenous. How do we even search for proofs? Well, we use a language model, and the goal of that first paper was really to answer, does it even work? Yes, it works. We get up to, as we can see, 50% coverage of that formal system. At the time was MetaMask, but the numbers are roughly the same on Lean. We get to 56% performance. That performance doesn't really necessarily means a lot. The reason why is because if you take a math library, you take a test set of the theorems in there. There's those statements, those theorems, they've already been splitted by humans so that the formal proof are not too big. And so there's actually a very large amount of intelligence that is embedded in the set of statement itself, in the sense that each of the statement is not a proof of a very necessarily a proof of a very challenging theorem. It's generally a technical lemma that has been engineered by humans to provide cuts that are useful to keep the proof small. So that means that only means that those models can be of good assistance to humans as they formalize, because one of two times when they were to submit a statement to the system, they could get a formal proof in exchange successfully, which could be useful to help accelerate formalization. But the real interesting part is to study how that performance evolves as you change parameters of your experiments. And so our second paper that we released a months ago is really about addressing that lack of self-play, which leads to a lack of curriculum. So that paper states that in the introduction. I'll read it because I think I spent a lot of time writing it, and I think it's a good summary of the idea. And basically, the basis for addressing the lack of self-play is the observation that the key role of self-play is to provide an unsupervised curriculum. That's why I try to explain. You play against yourself, so you're playing against something that has the same strengths as you have, and through exploration you get slightly better and better, and that provides a very smooth unsupervised curriculum. We propose instead to supply for formal math an auxiliary set of problem statements without requiring proof of varying difficulty. And we empirically show that when the difficulty of these auxiliary problems is varied enough, a simple expected iteration procedure is able to solve a curriculum of increasingly difficult problems. So the idea here is to say, we have a bunch of problems that we care about and that are too hard to us. We have no way to reframe the problem to generate easier statements, or no easy way to do so. So let's just bite the bullets and formalize a bunch of statements that are related to the problems we care about, and that are of varying difficulty. What does it mean in practice? In practice, we were really caring about that benchmark mini F2F, which is a set of Olympiad problems. And so some of those Olympiad problems are easy. We were able to find proofs. Some others are really hard, and we're completely unable to find proof. How do we create an auxiliary set of statements that is of varying difficulty? Well, we take books that are used by humans to train for Olympiads, and we formalize as many statements as we can from those books. So basically, we were caring about Olympiads, and the way to provide a curriculum to our own systems was to go find the books that humans use to train and just formalize the statements. And why we can only formalize the statement is because we are in formal land, and so we have a perfect verifier. And so if the model managed to close one of those statements, that means that we've generated a proof that we can use as good training data. And that's what it's meant by expert iteration. The process of expert iteration is really to take a system, make it produce trajectories, so in our case, formal proof, and take those generated proof and retrain on those. And as you do that, the system gets a little bit better. And you keep doing that, it will close more statements from that curriculum. You get new proof, you retrain, and you keep iterating that way. And what we just simply showed is that it actually works to do that. If you provide an auxiliary curriculum of just the statements and you don't need the proof here, the model through expert iteration is capable of closing increasingly difficult problems and get better and better. And eventually that performance transfers to the benchmark we care about. So this is an example. These are actually curves about expert iteration on MassLib itself. So MassLib is and MiniF2F. So here what we do is that we take the trainings, we have a training set with proof. We train on it. We have the test sets on these statements, right? And what we do is that we take our models, train on the training sets. We take that training set and we remove all the proof. And we try to generate new proof from our models on the statements coming from the training sets. And the model will find a bunch of, will not find all the proof because we have a bunch of regularization that makes that it doesn't remember everything, but it generates a bunch of new proofs. And we train the model on those newly generated proof from the training sets. And they'll be varied. Basically, it will find different ways of proving the same thing from the same training statements from the training sets. And we run that expert iteration only on the training set from MassLib. And what we show is that the performance on the valid set of MassLib actually increase smoothly and nicely, going from 55% to 63% as you do 3 iteration. And we, at the same time, we evaluate the performance on the benchmark we care about, MiniF2F, and we see that it doesn't transfer as well, right? Here it's pretty stable. Eventually, you have kind of a nice kick at the end, but it doesn't transfer that much. But you see that expert iteration kind of works on MassLib valid and kind of transfers a little bit on MiniF2F. This curve here, I'll try to explain briefly. This is an ablation because as you do expert iteration, you deploy compute. You deploy compute for generating the proof. You deploy compute for training the model. And as I've mentioned before, if you have more compute, you can try proving statements more times, and it generally leads to better performance. So here it's really an ablation of if you use the same amount of compute, what happens if you're just trying to prove statements from MassLib valid, right? Versus running expert iteration. And as you can see, that expert iteration has a much higher rate of improvement. And this dotted line here is because it's a way to shift that curve up to compensate for the compute we expend for training the model. So basically, the real comparison is here. There is a regimen where if you allocate all your compute to making more attempts, you'll be better than running expert iteration. But quickly expert iteration, which means retraining the model on new data generated, new synthetic data generated by the model itself, actually leads to better performance. So those two curves shows that expert iteration really has a nice visible effect in terms of performance. And so here, this is the same experiment, but on MiniF2F valid, while using the statements that we formalized. So as I said, the statement formalized is a bunch of statements from books used by humans for training for the Olympiads. MiniF2F is a benchmark that is the formalization of the statements of Olympiad problems. And we care here, this is a comparison here between the expert iteration only running on MassLib train versus expert iteration that runs on MassLib train plus the statements that provide as a curriculum. And you see kind of an interesting shift. And basically the conclusion of that paper is to say that we don't have a curriculum in a way to have to generate a curriculum for self-informal math for hard problems. But if you are capable of formalizing statements only from the same distribution that you care about, well, it's possible to have the model climb that curriculum of statements by itself through retraining itself on its own generations in a way that is productive. And you basically, by providing just statements, you're basically capable of shifting the distribution of the model where you want it to be. And this is kind of exciting because it reduces, if you really believe in it, it kind of reduces the problem of getting better at a distribution you care about to generating statements instead of training proofs. And generating statements is much cheaper than generating proof. Basically, generating a statement when you kind of trained informal systems will take you 5 to 10 minutes, whereas generating a proof for that statement will probably take you more like 30 minutes or an hour, depending on the statement, obviously. So it's kind of yep.
Yeah, quick question. How large are the data sets, in particular also the synthetic one that you?
It's actually, so what do you mean by synthetic? They're not synthetic because they were manually formalized, but
that you just the proofs that you formalized from the books, essentially. Like
the statement. So the statements, not the proof. Yeah, it's actually rather small. It's something like 300 statements.
Okay.
It's not that big. So knowing that in massive train, as an example, we have 50,000 statements. So just adding 300 statements out of 50,000 statements that you use to run your expert iteration loop really actually shift the distribution nicely towards what you care about. And another thing that you can think of that we haven't started studying necessarily is that you could hope that translating from informal statement to formal statement is something that is easier than generating proof. And so you could leverage machine learning and machine translation actually to actually generate even more statements in a fully synthetic way. This way, removing the human from the loop. You could scrape AOPS. AOPS is a website where all the Olympiads are stored, and you have a lot of discussion around them. You could scrape AOPS and hope to train a translator between informal and formal, and there will be a new set of statements that you could use to do reinforcement learning on top of that and get even better performance on the F12. All right, so that's.
May I ask?
Yeah, sure.
A priori, it wasn't clear that sort of things that humans find hard or difficult is also the thing that the algorithm will find easy or difficult in the end. I mean, as I said, that it showed some preference for smaller kernel sizes, so it might be that so there's a simple argument for a human that makes this problem easy that sort of would require many steps in the formal language, so it's sort of deep down in the search tree or something. So the fact that this works is not completely guaranteed, or
obviously, and we're really just scratching the surface in a sense. Basically, all models are capable of solving some problems that I'm completely incapable of solving. Some inequalities that are challenging, definitely challenging to me, and they also fail like really badly on statements that are really just trivial to me. And so it's definitely right that first it's unclear what you transfer and what you learn, and it's also not obvious exactly what is hard in formal land versus what is hard in informal land for sure. But this is an example of a statement. So this is a kind of a somewhat challenging inequality. This is the formalization, and this is the proof that was found by the model. It's a rather simple proof. It calls the n-linearis tactic. N-linearis, if you call it alone, will not solve that statement. And so what is really nice here is that we really leverage so first through expert iteration, the model has learned to really squeeze as much performance as it can out of n-linearis. And as you can see here, it's capable of generating arguments to n-linearis that are somewhat exogenous and that are necessary to really direct n-linearis in the right direction to solve that problem. So here you really see kind of something that proof is really hard to normal humans. It's kind of easy for the model because it's kind of through expert iteration, it has learned to use n-linearis very efficiently. And so here you have an example where it prompts n-linearis with things that are not necessarily obvious to a human, even that formalize a lot of whether it would work, and provide those arguments and solve the problem in one tactic application. Here, this one is another example. It's kind of nice for two reasons. First, you have really two main reasoning steps. So this is kind of mostly shuffling stuff around. You have one call to contrapose, which kind of use contraposition. And then you have this use 0. Basically, the tactic stakes at this point is there exists something such that, and the model say, I'm going to provide a witness, and the witness is 0. And so that 0, you could make the argument that it exists in the state. There's a 0 here, so you could just try it. But it's kind of nice to see the model generate actual terms that are used for existential proof. So it's kind of nice, and then it concludes by applying a few set of tactics. This one is kind of nice because you really have a few reasoning steps that are really non-trivial. And there, this is another example. This one is not super nice. It's very noisy. I think you could really compress that proof if you wanted to have a very nice version that would be at the level to be committed to MathLib. What is interesting here is that the half tactic is about introducing cuts. So here it's really dealing with that n over n plus 1. And so it says, hey, I'm going to prove, because I'm going to need it later, that n plus 1 is different than 0 in our case, so that I'll be able to divide by it. And so it really introduces that's very simple, but still nonetheless a cut, and proves it at the next. Here is the proof of that cut, and then the proof keeps going. So that gives you an idea of, and to go back to the aesthetics of proofs, this proof would be considered really ugly by anybody reviewing it for being committed into MathLib. So sometimes it finds interesting proof, sometimes it finds ugly proof, but really right now we're really caring about finding anything, which is already exciting. To give you an example here, this one is also to make the same points. This is a kind of a human formalization of a problem on the left, and this is a solution found by the model. So sometimes the model finds kind of not short. I mean, it's not necessarily more elegant because this one is easier to read, but it's more compact. Since we have a few minutes, I can show you a small, if you're interested, I can show you a really quick demo of what it generates for a few simple problems. I'll give you an idea. I'll stop sharing and I'll reshare another window. And in the meantime, if you have any question, I'm happy to answer them as well. Let me make these things bigger. Are you able to see everything? Cool. So this is a kind of a bunch of very easy proofs, and with the actual informal proof. And we've built a tactic in Lean that actually calls our model and makes suggestions about what to prove. So I'm calling it GPTF. And what it answers, it says, hey, you should. So this is all the predictions from the model. And the successes are the ones that have been accepted by the formal system. Doesn't mean that they'll lead you to a proof. It means that just they are syntactically correct and they unify to the current goal. And those ones are, all the predictions are other predictions that didn't play out. As an example, exact, if you were to try it, the model, the formal system will give you an error. Going back to it, we can kind of use it. And so here it says, well, you see, here it says exact. Exact is when you actually provide the kernel level term directly. And since it's been valid, it feels like it's going to be correct. And so I'm using it and I've accomplished my goals. So as you can see, this is the kind of interaction you can have with the model. And that gives you an intuition about the kind of proposition that it makes. So as an example here, it generates all those different tactics. They're all invalid. There's also this one that is valid. Let's see what it gives us. It actually closes the goal. Here it's an example where you need to, the most easy way is to generate a witness. It's really, there exists n such that 4 equal to n. It's a very easy witness. As you can see, the model is capable of generating a tactic that actually generates that witness. That's kind of nice and fun. The nice thing about that, the fact that we're using a generative language model is that you can prompt the model and tell it to say, you can tell it, please just generate tactics that starts with this. And so here we're just telling him, please generate only kernel level terms, just use the tactic exact. And so here it made a bunch of predictions, none of them are correct. So I can just try again. Still incorrect, a bit depressing. Still incorrect. Still incorrect. So as you can see, that's a good example here where trying many times, since you have a formal system in front of you, can try many times, and the formal system will give you a feedback, and you eventually might land on the right one. So here I've tried 4 times. It generated something like 16 or 10 or 8 different tactics at each time. And it's only at the 4th time that I do generate a valid one, which actually indeed closed the goal. So that gives you kind of an idea of the kind of generation that the model will make, and what is the experience playing with it as you formalize as well, and how it can help the formalization effort on top of trying to close to make progress on specific benchmark. All right, that's all that I had. I'm happy to take any questions if you have any.
Thanks a lot for this very interesting talk. Other questions?
Yeah, maybe I have a question then. Did you think of ways to try to encourage shorter proof, assuming that shorter proof are often better than longer one, maybe playing with the reward function, instead of just 0 and 1, something that it cannot just be the length of the proof, because some mathematical statements require long proof, but something around that?
Yeah, so one thing that I didn't cover here, but we've been experimenting with, is that as we do tree search, we actually also train a value function to guide that tree search. And one of the value functions we experimented with is actually to try to model the size of the proof needed for a given goal. And so that's really kind of exactly trying to favor shorter proof, because you're going to be favoring states as you do tree search that are expected to lead to shorter proof, because they're supposed to get you closer to the answer. And so using that value function they provide kind of a nice boost, but it's really challenging to, at least in the current state of affair, it's really challenging to model that signal correctly. And so far, our value functions have been kind of not weak, but not the greatest. And so it's really been a challenge so far to train a really good value function in that space. And so to train that value function, as we do that expectation, we have the original data, we have a bunch of generated data, and for each goal, we record the size of the proof, and we use machine learning to model that signal, and that becomes a value function for the goals, because when you expand your tree, you have a bunch of goals, you need to prioritize them, and you just pick the one for which the model thinks the proof is going to be the shortest.
Thanks.
I think there are also 2 questions in the chat. So
yep.
maybe I can read one out. This is one from Mehdi. Is it possible to use these models to do similar tasks in chemistry or physics, such as designing experiment or proving theorems? Yeah. So what do you think?
So in chemistry or physics, the challenge is that if you don't have a formal system to that you can to apply all of these, it all relies on having a formal verifier that will give you a final decision whether what you generated is good or not. To me, intuitively, but I'm not an expert, physics seems to really land into the informal land of things, because you probably, it's probably very challenging to create a verifier. You would probably have to have an experimental setup that you link to that would run the experiment in the loop and give you whether the experiment results are aligned with the prediction you made on the physics side of things. So I think it really more, to me, physics and chemistry really more lands into the informal space, which is even more challenging, because it's all the same, except you don't even have a verifier.
And then there's this second question. Did you consider generating the theorem statements from the language model itself?
Yeah, so we definitely explored that a little bit, but then we're excited to push more there. You can definitely use the language model to generate statements. It's as easy as, instead of prompting it with declaration name, goal, and proof step, and it gives you the tactic, you just give it declaration name, and it's generally human readable, so you can make up some names, and the model will gladly generate a goal for you. And it's going to be a statement that you could try to prove. The challenge there is that to generate data out of that, you have to not only generate the statement, and then you have to attempt to prove them, And it's only when you prove those statements that it's a new good data. It means that not only the statement generated was valid and true, but also that you have a proof for it. And so it all depends on how good your conjecture is. If your conjecture generates one provable by your model and true statement out of 1,000, you'll be expending a lot of compute on those 999 other statements to try to prove them, all that to get just one new data point. And so there is really a challenge here, because if that fraction of statements that are actually provable by our models and true is very low, then it's really compute expensive and leads to not being useful to generate data. But if you get your model to a state where it generates good statements or interesting statements to generate new data at a rather high fractions, then it's a really good source of statements and a really good source of new proofs and then new data.
Yeah, so I have a question on also again, generating more theorems, more proofs. So I mean, when people look at language models, say to solve differential equations or so, they generate large data sets effectively to train these models. And is this something that is also helpful for you, or would be helpful for your models, or it's because it's a slightly different domain in the sense, like when I look at your statements compared to
so basically, when you're proving in formal land, you're generally proving in a backward fashion. You start from a statement and you apply tactics to have new goals that are slightly easier all the way to landing into true. What you could do, it's somewhat challenging to do in lean, but it's easy to do in other formal systems, is you could do forward proving. And forward proving is basically you take things that you know and you use them as arguments to other theorems that you know, and generates you a new statement, and you keep going like that, and that generates synthetic data that you can then go you look at in a backward way eventually, and it gives you a new data. We've been playing with that in MetaMass, which is another formal system where it's really easy to do. It hasn't led to being that useful because the kind of data that you generate is really noisy, and your exploration really goes all over the place into stuff that are not necessarily really interesting, but we haven't pushed that much. And that's actually a result from DeepMind, Vlad Firiu. He kind of studied guiding saturation-based solvers like eProver. So that these are kind of the symbolic reasoning provers, state-of-the-art, guided with machine learning. And to generate the data set to train the machine learning based guide for the saturation algorithm, we actually used exactly that trick of doing forward reasoning and generating clauses without going for a goal, and use that data. So yes, it's definitely interesting and doable.
Okay, yeah, down the line you have one, so you basically have language on there, right, where you don't have something. Can you see already some potential application, where, being able to, to do formal math?
I think the reason why OpenAI is interested into formal math is because it is really like language, but with the access to a verifier. So if we really manage to make really good progress in that space, we'll have solved 2 of 3 problems basically, and then you can hope to be able to train an informal verifier. You could train a model to say whether an informal proof is good or not. It would probably not be perfect, but if you've solved all the other problems, then you can focus on this one. And so that's the reason why it's kind of a well aligned with our mission. And yes, eventually the goal is to probably have learned verifiers instead of formal verifiers.
Right. Yeah, cool. Yeah, thanks a lot for the talk. I can see no more further questions coming up. So yeah.
Thank you very much for having me. It was a lot of fun, and I hope you liked it.
Yeah, thank you. It was very interesting.